So today we're going to be doing Feb March 2024 paper 12. Question number 1 says, which species contains the same number of neutrons as carbon 14 and the same number of electrons as Na plus? So carbon 14 has 8 neutrons, right? Because the mass number is 14, mass number is protons plus neutrons, the proton number is 6. That means we have 8 neutrons. And this guy has 10 electrons, right? An atom of sodium has 11 electrons, but we've lost 1 electron, so this has 10 electrons, right? So which of these guys contains 10 electrons and 8 neutrons? The answer here is D, right? We have 8 neutrons, 16 minus 8, right? So that's 8 neutrons. And then here we have 8 plus 2, which is 10 electrons, right? Because an oxygen atom has 8 electrons, so oxygen ion, the oxide ion will have 10, right? 8 plus 2 has a 2 minus charge, so it's gained 2 electrons. Which process has the largest enthalpy change per mole? Now, one thing you notice over here is that Al3 plus, P5 plus, S6 plus, and Si4 plus, all of these guys have 10 electrons. All of these guys have 10 electrons, right? So you remove 3 electrons from aluminum, aluminum has 13. You removed 5 from phosphorus, phosphorus has 15, now it has 10. Sulfur has 16, you removed 6, so it has 10. And then silicon has 14, you removed 4, so now you have 10. So all 4 of these have 10 electrons, right? All 4 of these have 10 electrons. So that means they have 2 complete shells. So you removed all the valence electrons from all of these atoms. Okay, you removed all the valence electrons from all of these elements. You have these ions. Now the question is saying, in which case would the most energy be needed to remove the next electron? Now, since all of these guys are isoelectronic, right, all of these guys have the configuration 1s2, 2s2, 2p6, right? All of them have the exact same configuration. They all have the exact same configuration. So when we talk about the ionization energy in each of these cases, removing the next electron, right, the shielding and the number of shells is not a factor here. So we're looking at nuclear charge, right? And we know that the sulfur atom has the greatest nuclear charge, right? We have 16 protons in the nucleus. The greatest number of protons in the nucleus is sulfur from all of these elements. Now, since all of them have the same configuration, same shielding, same number of shells, but because this has the greatest nuclear charge, the most energy is needed to remove the electron from S6+. So the answer is C. Question number 3 says, which sodium compound contains 74.2% by mass of sodium? Start with sodium carbonate. Sodium carbonate is Na2CO3, right? We have 2 sodiums here, so that would be 2 times 23, that's 46, divided by the total MR, which is 46 for the 2 sodiums, plus carbonate, which is 60. 12 plus 3 times 16, that's 48. 60 plus 46, right? So that's 106. If we were to multiply this by 100, right, the answer that we get will give us the percentage by mass of sodium. In this case, that doesn't come out to 74, so we can just move on to the next part. Sodium chloride is NaCl. Here we have 1 sodium, so that's 23. The MR is 58.5, 35.5 for chlorine plus 23 for sodium. Multiply that by 100. Again, you're not going to get 74%. Okay, so don't need to worry about that, right? Because the reason I'm canceling these out is because we know for a fact that these are below 50%, right? We know that this mass of sodium is less than half of the total. This mass of sodium is less than half, right? So we don't even need to worry about doing the calculation, right? Just by looking at the fraction, we can tell that it's less than 50%. Sodium hydroxide is NaOH, right? For NaOH, we have an MR of 40, we have 1 sodium, so we have 23 for sodium divided by 40, right? OH is 17 plus 23, that's 40, times 100. Okay, this doesn't come out to 74.2% either, so the answer has to be D. Okay, sodium oxide, here the formula is Na2O. We have 2 sodiums, so that's 2 times 23, so that's 46, right? 2 times 23, that's 46, divided by 46 plus 16 for oxygen, so that's 62 times 100, and this comes out to 74.2%. Okay, so the answer here is D. What is the maximum volume of sulfur dioxide gas measured at room conditions produced from burning 100 decimeter cube of diesel fuel, 100 decimeter cube of diesel fuel containing 0.8346 grams of sulfur? Now over here, this piece of information given to us, the 100 decimeter cube, this piece of information is irrelevant. We don't really care about this piece of information. What they've given us is the mass of sulfur in this compound. They've given us the mass of sulfur in this compound. So we have 0.8346 0.8346 grams of sulfur. And we know that all the sulfur is being converted to sulfur dioxide, right? Because when sulfur is combusted, it converts to sulfur dioxide, right? We don't get sulfur trioxide. The reason we don't get sulfur trioxide is because the activation energy needed to make sulfur trioxide is very high. So we need a catalyst to form sulfur trioxide. So what we know is that all the sulfur is being converted to sulfur dioxide. So we can say we can find the number of moles of sulfur. The number of moles of sulfur is the mass divided by the molar mass. So that's 0.8346 divided by the atomic mass of sulfur, which is 32.1, which is 0.026 moles. 0.026 moles. So we have 0.026 moles of sulfur, and we're getting the same number of moles of sulfur dioxide, 0.026 moles. Okay, we have 0.026 moles of sulfur dioxide. We need to find the volume at room temperature and pressure of sulfur dioxide. We have the moles. You know that the volume in centimeter cube. You know that the volume in centimeter cube is the number of moles times 24,000, right? Where 24,000 cm cube is the molar volume of a gas. So that is 0.026 times 24,000, which comes out to 624 cm cube. So the answer is D. Okay, the answer is D. Which row shows the correct number of covalent bonds in a molecule of methylpropene? So let's first draw out the structure of methylpropene. We have a 3-carbon chain, right? That's propene with a double bond. So we have a 3-carbon chain like this with a double bond. We have a methyl group. The methyl group must be in the middle, right? So we have a methyl group here, and then we draw out the hydrogen. So we have a CH3, we have a CH3 here, and then we have 2 hydrogens over here, right? So we have C4H8. The total number of sigma bonds here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 sigma bonds. So we have 11 sigma bonds. Remember, single bonds are always sigma bonds, and double bonds are sigma and pi bonds. So we have 11 sigma bonds, and we just have 1 pi bond, right? We have a double bond here, which is a sigma bond and a pi bond. So single bonds are always sigma bonds. We have 10 single bonds, and then we have 1 sigma bond here, right, in the double bond. So that's 11 sigma bonds, and we have 1 pi bond. Okay, so the answer is C. Question number 6 says, aluminum chloride exists as Al2Cl6 molecules at room temperature. When heated to a high temperature, AlCl3 molecules are formed. What are the arrangements of the bonding pairs of electrons around the aluminum atom in the 2 forms of aluminum chloride? Now in aluminum chloride, we have AlCl3, right? We have AlCl3. The aluminum is bonded to 3 atoms. Okay, the aluminum is bonded to 3 atoms, right? And it just has 3 valence electrons. Aluminum has 3 valence electrons. All 3 of those electrons are bonded. So it's just 3 atoms bonded, and there's no lone pairs. So if we just have 3 atoms, right, we have a trigonal planar shape, and bond angles are 120 degrees, right? This is trigonal planar. So AlCl3 must be planar. And then in Al2Cl6, we have something like this, right? Let me remind you guys, what happens is that in Al2Cl6, right, the 2 AlCl3s are bonded together, right, because we have the formation of dative bonds. The chlorine from one AlCl3 molecule combines with the aluminum from another, and same thing here. The chlorine from the second one combines with the Al of the first one, right? So this chlorine donates a pair of electrons, forms a dative bond to this aluminum. This chlorine donates a lone pair, forms a dative bond with this aluminum, right? So what you notice here is that each aluminum is bonded to 4 atoms. So each aluminum has a tetrahedral geometry. So the answer is B. The table shows the physical properties of 4 substances. Which substance has a giant covalent structure? Now, obviously it's not A or B, because A and B have very low boiling points and melting points, right? Giant covalent structures would have very high boiling points or melting points. But we know that if it's giant covalent, it would be a poor conductor in the liquid state, right? If it's a good conductor, that means it's ionic, right? This is ionic. So it can't be C either, right? So it must be D, right? It must be D. So ionic compounds are good conductors in the molten state because you have mobile ions, right, that are free to move. But macromolecules do not conduct in the molten state. At room temperature and pressure, H2O is a liquid and H2S is a gas. What is the reason for this difference of state? So in other words, the question is asking, why does H2O have a higher boiling point? Right? Why does it have a higher boiling point? Why is it a liquid at room temperature? The reason it has a higher boiling point is because we have hydrogen bonding between H2O molecules, right? Why do we have hydrogen bond? Because we have a hydrogen directly bonded to an oxygen. Remember, if a hydrogen is directly bonded to an oxygen, nitrogen, or a fluorine, in that case we have hydrogen bond. So in the case of H2O, we're going to have hydrogen bonding. So the answer here is C. There is significant hydrogen bonding between H2O molecules, but not between H2S molecules. The enthalpy change for a reaction can be calculated from values of enthalpies of formation, enthalpies of combustion, or bond energies. The enthalpy change of the reaction given is equal to delta HR. So this is the reaction that they've shown. Which expression could be used to calculate the enthalpy change of the reaction? So if there's a reaction for which you want to find the enthalpy change, right? If you're given a reaction for which you want to find the enthalpy change, if they've given you enthalpy change of formation data, we can say that the enthalpy change is equal to the enthalpy change of formation of the products, okay? The enthalpy change of formation of the products minus the enthalpy change of formation of the reactants. So for any given reaction, if the formation data is given, you can say the enthalpy change is the formation of products minus the formation of reactants. Now here, if you look at option D, right, you might think that's the answer, but that's not the answer. The reason why is because here you would have to take the stoichiometric coefficients into account, right? Because here we have 2 moles of methane. So when we talk about the enthalpy of formation of the products, we have to do 2 times the formation of methane. We have to do 2 times the formation of methane plus 2 times the formation of carbon dioxide plus 2 times the formation of H2O, because we have 2 moles of each of these. Then we have to subtract 2 times the formation of ethane, right? The enthalpy change of formation of oxygen, which is an element, is 0, right? The enthalpy change of formation of elements in their standard states is 0. So we don't need to worry about that. But this is not the answer. The reason why is because we haven't multiplied with the stoichiometric coefficients. Now, if you've been given combustion data, for the products and the reactants of a particular reaction, right? Again, you want to find the enthalpy change of a particular reaction. If the data given to you is the combustion data, which you can say that the enthalpy change of that reaction is the enthalpy change of combustion of the reactants minus the enthalpy change of combustion of the products. So now here your reactant is ethane, right? And we have 2 moles of that. So we're going to say 2 times the enthalpy change of combustion of ethane, right? 2 times the enthalpy change of combustion of ethane minus the enthalpy change of combustion of the product, right? Obviously, oxygen doesn't undergo combustion. Oxygen is needed for combustion, right? Carbon dioxide and H2O can't be combusted. CO2 and H2O can't be combusted. They're combustion products, so you can't combust them further. So we only have to worry about methane, right? So our reactant here is ethane. So we have 2 times the combustion of ethane, that's reactants, and we subtract the combustion of products, so that will be 2 times the combustion of methane. And the answer then is B, right? We have 2 times the combustion of ethane minus 2 times the combustion of methane. Which reaction has an enthalpy change equal to the standard enthalpy change of formation of propane? When we talk about standard enthalpy change of formation, the standard enthalpy change of formation is the enthalpy change when 1 mole of a substance is made in its standard state from the elements in their standard states. Now we know that propane is a gas in its standard state, right? At room temperature and pressure, propane is a gas. Remember, the first 4 alkanes are gases. So methane, ethane, propane, butane are gases, right? So we know propane is a gas, which means that option D is definitely not an option, right? Because we're making propane in the liquid form here. So that's not an option, right? And then the elements have to be in their standard state. So we want to make 1 mole of propane gas. We want to make 1 mole of propane gas from the elements in their standard state. The only option which the elements are in their standard states is option C, right? Carbon is a solid in its standard state, right? Graphite is taken as the standard state of carbon, and then we have hydrogen gas in a standard state. So the answer is C. One of the reactions in the rechargeable lead acid battery is shown. Which statement about this reaction is correct? So option A says lead is both oxidized and reduced. Okay, well, let's check. Here lead is 0, right? Because an element in its standard state has an oxidation state of 0. Here lead is plus 4, right? Because we have 2 oxygens, minus 2 each, so that's minus 4. So that means lead must be plus 4, right? Because the overall is 0. So 2 oxygens minus 2 each, so that's 2 times minus 2 minus 4, so that means lead is plus 4. And then over here, lead is plus 2, right? Because the sulfate ion is minus 2. Sulfate is minus 2, that means lead must be plus 2. What we see here is lead is being oxidized from 0 to plus 2 and it's being reduced from plus 4 to minus 2. So the answer is A. KMnO4 is an oxidizing agent. Its reaction with Fe2 plus is shown in the following ionic equation. What are X and Y when the equation is balanced? Now over here we have a redox reaction, right? We have a redox reaction. Manganate 7 is the oxidizing agent and it's oxidizing Fe2 plus to Fe3 plus, right? So what we have here is this, right? What we have is, we talk about what's being oxidized, right? Fe2 plus is being oxidized to Fe3 plus, right? So that's a change of plus 1, okay? That's a change of plus 1. And when we talk about what's being reduced, right? We have manganese going from plus 7, right? We have manganese going from plus 7, right, to plus 2, right? It's going from plus 7 to plus 2, right? So in MnO4 minus, the manganese is plus 7, right? We can check that if we have MnO4 minus, right? We have MnO4 minus. Let's say manganese is X. We have 4 oxygens which are minus 2 each. We have an overall oxidation state of minus 1, right? So that gives us the oxidation state of manganese as plus 7, right? So manganese is going from plus 7 to plus 2. So that's a change of minus 5. The oxidation state is decreasing by 5. So that's a change of minus 5, right? Or in other words, we can say that it's gaining 5 electrons, right? And iron is simply losing 1 electron. So to balance this, right, we're going to need 5 over here for every 1 manganese, right? We're going to need 5 irons for every 1 manganese, right? Each Fe over here is losing 1 electron. So 5 of them will lose 5 electrons and then 1 manganate 7 will gain 5 electrons, right? The changes in oxidation number have to balance, or the gain and loss of electrons has to balance. So we can say we're going to need 5 Fe's for every 1 MnO4 minus for the gain and loss of electrons to balance. So we need 5 Fe's, for every 1 manganate 7. That means X is 1 and Y is 5. So the answer is C. Nitrogen and hydrogen are mixed in a reaction vessel. The reaction reaches equilibrium, giving a mixture of nitrogen, hydrogen, and ammonia gases. The mixture of gases present at equilibrium at a total pressure of 300 atmospheres is shown. What is the equilibrium constant Kp for the forward reaction? Remember, Kp is the partial pressure of the products, in this case that's ammonia, squared, right, to the power of the stoichiometric coefficient, divided by the partial pressure of the reactants. So we have partial pressure of nitrogen times the partial pressure of hydrogen cubed, right, because again to the power of 3. Okay, now what is the partial pressure? The partial pressure is the mole fraction times the total pressure. And what is the mole fraction of a gas? The mole fraction of the gas is the moles of that particular gas divided by the total number of moles. Okay, so let's first figure out the total number of moles here. We have 180 plus 590 plus 160, that's 930 moles. 930 moles. So that means that the partial pressure of ammonia, right, the partial pressure of ammonia is the mole fraction. That would be 160 divided by 930, 160 divided by 930 times the total pressure, which is 300, right? So that's squared, right, for Kp. That's the partial pressure of ammonia squared divided by the partial pressure of nitrogen. That would be the moles of nitrogen, that's 180 divided by the total number of moles. So 180 divided by 930 times the total pressure, which is 300. And then for hydrogen, we have the moles of hydrogen divided by the total moles. That's the mole fraction. So 590 divided by 930 times the total pressure, the whole thing cubed, right? Partial pressure of nitrogen times partial pressure of hydrogen cubed. And this gives you the value of Kp as 6.65 into 10 to the power of minus 6. So 6.65 into 10 to the power of minus 6. So the answer is A, right? For the units, you can just do pressure squared. For the units, you can say The units are pressure squared in the numerator divided by pressure to the power of 4. So that would be 1 over pressure squared. In this case, the pressure is given in atmospheres. So that's pressure to the power of minus 2, which is atm to the power of minus 2. The units are atm to the power of minus 2. A mixture of hydrogen gas and iodine gas is placed in a reaction vessel of volume V at temperature T. The reaction H2 plus I2 react to give you 2HI is allowed to come to equilibrium. Is a reversible reaction. All substances remain in the gaseous state. Argon gas is then pumped into the reaction vessel. The temperature in the vessel is maintained at T. How are the rate of the forward reaction and the partial pressure of HI at equilibrium affected? Now over here, when argon gas is pumped in, the total pressure of the reaction vessel increases. Now over here, because we have the same number of moles of gas on either side, right? We have 2 moles of gas here, 2 moles of gas here. An increase in pressure does not affect the position of the equilibrium. Furthermore, the partial pressure is the mole fraction times the total pressure, and we know that the mole fraction is the number of moles of gas divided by the total number of moles. When argon is pumped in, the total number of moles of gas increases, which of course means that the mole fraction decreases, but at the same time the total pressure is increased by the same proportion. Total pressure is increased by the same proportion, so the decrease in mole fraction and the increase in total pressure cancel each other out, so the partial pressures for all the gases remain constant. So the partial pressures of HI and hydrogen and iodine are unaffected. Another thing to notice is that because the equilibrium position doesn't change, the number of moles of all the gases remain the same, and therefore the concentration remains the same because volume is constant and the number of moles is constant. So concentration is unaffected, the partial pressures are unaffected, and the temperature is kept constant. So all the factors that would affect rate do not change, so the rate is unaffected. So the answer is D. 2 experiments are carried out to study the reaction between zinc and sulfuric acid. In experiment 1, small lumps of zinc are added to excess dilute sulfuric acid. In experiment 2, the reaction is carried out at a lower temperature and with one other change. Both experiments produce the same total volume of gas and are completed in the same time. So in other words, the rate is unaffected. Okay, the rate is unaffected. Okay, so there's no change in rate. Okay, there is no change in rate. Now we know that in experiment 2, decreasing the temperature would decrease the rate. So the other change must have increased the rate. Okay, the other change must have increased the rate, right? Because if we're decreasing temperature, we're decreasing the rate, so the other factor must have increased the rate. Now what factor could increase the rate here? Well, one factor that could increase the rate is the use of a catalyst. So the answer is A. Okay, because a catalyst increases the rate of the reaction, right? Without itself being changed at the end. So it increases the rate by providing an alternative mechanism or pathway with a lower activation energy, and itself is not used up. Okay, the mass of zinc wouldn't really affect it. Larger lumps would slow it down, and a greater volume of sulfuric acid would not affect it either because sulfuric acid is already in excess. A greater concentration would increase the rate, but not volume. The relative magnitude of the property X of 5 elements is shown. P, Q, R, S, and T are all in period 3 and have consecutive atomic numbers. The letters are not the actual chemical symbols of the elements. Which row is correct for property X and element R? Now this graph, okay, is the graph for electrical conductivity, right? What we have here is we have sodium, magnesium, and then aluminum, right, in period 3. Okay, we have sodium, magnesium, aluminum in period 3. Those are the metals. They have relatively high electrical conductivity, and then we have the non-metals which have a much lower conductivity. So property X is electrical conductivity and element R is aluminum. Okay, element R is aluminum. So the answer is A. Now, melting point follows a similar looking trend. Okay, melting point follows a similar looking trend, but it looks like this. Okay, the melting point trend looks like this. So you have an increase from sodium to magnesium to aluminum to silicon, right? Because you're going from metals to macromolecule, right? You're going from metallic bonding to macromolecules, right? Or giant covalent structures. Silicon has a very high melting point. And then you have a drop to phosphorus. And then you have an increase again to sulfur, because phosphorus is P4 and sulfur is S8, right? These are your simple molecular substances, right? These are your simple molecular substances. So you have Cl2 and then argon, right? So this is what the melting point trend looks like. You have an increase all the way up to silicon, but then you have a decrease to P4, and then you have an increase again because S8 has more electrons than P4. You don't see that increase over here. Okay, you don't see that increase over here, so this is not the melting point trend. Okay, this is the electrical conductivity trend. Element X is in period 3. Element X reacts with oxygen to produce a solid Y. When solid Y is added to water, a solution with a pH of less than 7 is produced. So we have an acidic oxide. Okay, we have an acidic oxide. An acidic oxide. Which of these guys would produce an acidic oxide? Well, sodium oxide is basic, so that's incorrect. Silicon dioxide is acidic, but it does not dissolve in water. It does not dissolve in water, so it's not B. Phosphorus oxide is a solid, right? P4O10 is a solid that dissolves in water to produce an acidic solution, right? Phosphoric 5 oxide dissolves in water to produce phosphoric acid, right? Reacts with water to produce phosphoric acid. So the answer is C. Sulfur dioxide is also an acidic oxide, but it's a gas, right? Here we have a solid oxide being produced. So the answer is C. The question refers to isolated gaseous species. The species F minus, Ne, and Na plus are isoelectronic. Okay, they all have 10 electrons. This means they have the same number of electrons. In which order do their radii increase? Now again, remember that the greater the nuclear charge, the smaller the radius. The greater the nuclear charge, the smaller the radius. Fluorine has 9 protons in the nucleus, neon has 10 protons, and sodium has 11 protons in the nucleus. So sodium has the greatest number of protons in the nucleus, which means that in sodium there is the strongest attraction between the nucleus and the valence electrons. So therefore the valence electrons are held closer, which means that sodium is going to be the smallest. Okay, sodium is going to be the smallest, and then with fluoride we have the fewest number of protons, we have the smallest nuclear charge, which means we're going to have the largest radius. So the answer is C. Separate samples of magnesium and calcium are added to an excess of dilute sulfuric acid. The observations are summarized in the table. We have magnesium, which reacts vigorously, bubbles of gas are produced, magnesium completely dissolves. Calcium, we have a vigorous reaction initially, bubbles of gas are produced, reaction soon stops and leaves most of the calcium unreacted. Now what happens here is this, right? Let's say I have sulfuric acid, okay, I have sulfuric acid, and I have my metal, right? I have my metal that's reacting with the acid, okay? So let's say this is magnesium or calcium. Now when these guys react with sulfuric acid, a salt and hydrogen gas are produced, right? The salt would be either magnesium sulfate or calcium sulfate, right? In the case of magnesium and calcium respectively. Now, magnesium sulfate is soluble in water. So as magnesium sulfate is produced, right, it's dissolving in the solution. So all the magnesium will react. Now in the case of calcium, right, what happens is that the calcium sulfate as it forms a protective layer because calcium sulfate is relatively insoluble, right? It's relatively insoluble. So when the calcium sulfate forms, right, because it's insoluble, it essentially deposits over the calcium metal. It deposits over the calcium metal, preventing the calcium from reacting. So the answer is D. Magnesium sulfate is more soluble than calcium sulfate. Because calcium sulfate is less soluble, it forms a protective layer around the metal, preventing the metal from reacting. Question number 20. Dolomite is a double carbonate and can be used instead of calcium carbonate for treating acidic soils. The three statements all refer to the agricultural use of these carbonates. Dolomite and calcium carbonate are both less soluble than calcium hydroxide. Statement 1 is correct because we know that the carbonates are less soluble than calcium hydroxide. Calcium hydroxide is considered partially soluble, whereas the carbonates are considered insoluble. 1 mole of dolomite has the same neutralizing effect as 1 mole of calcium carbonate. That's not true because 1 mole of calcium carbonate just has 1 carbonate ion, whereas 1 mole of dolomite has 2 moles of carbonate ions. So dolomite would have a greater neutralizing effect. So statement 2 is incorrect, which means that the answer has to be B, right? Because 2 is incorrect, it can't be A, C, or D. We can still check statement 3. Dolomite and calcium carbonate both increase the pH of acidic soils. That is correct, right? They're going to neutralize the acid. They're going to neutralize the acid, make it less acidic. More acidic means lower pH, less acidic means greater pH. So statement 3 is correct. So the answer is B. This question is about two salts, sodium iodide and sodium chloride. The two solid salts are separately added to warm concentrated sulfuric acid and the results are noted. Aqueous solutions, the two salts are separately added to aqueous silver nitrate and then concentrated ammonia is added and the results are noted. Which row is correct? Now remember the first reaction, right? Concentrated sulfuric acid is a test for halides. We have chloride and iodide. We know that iodide is a stronger reducing agent. Iodide is a stronger reducing agent, right? Down the group, the reducing strength of the halides increases, right? It's easier for them to undergo oxidation, so they're stronger reducing agents. Easier oxidation of halides, easier to lose electrons because the number of shells increases, so stronger reducing agents. So iodide can reduce sulfuric acid, whereas chloride does not reduce sulfuric acid, okay? And iodide reduces sulfuric acid to hydrogen sulfide, right? It reduces sulfuric acid to hydrogen sulfide and itself is oxidized to iodine. Okay, itself is oxidized to iodine, whereas sodium chloride does not reduce sulfuric acid and itself is not oxidized. So it can't be A or B. And then silver iodide is a yellow precipitate that does not dissolve in concentrated ammonia. It does not dissolve in concentrated ammonia. So the answer is C. Question number 22 says the diagram shows the process of adding calcium nitrate and strontium nitrate to separate boiling tubes and heating them. Identical conditions are used. As the reactions proceed, the water containing universal indicator changes color. Which row describes the color change and identifies the nitrate that causes the quickest color change? Now for universal indicator, you guys should remember the colors of the rainbow, right? Roic Biv. Red being acidic, green being neutral, right? And then blue or indigo or violet being basic, right? So the more acidic it is, the more red it's going to be, and the more basic it is, the more blue it's going to be, right? And green is neutral. So the more towards the left, right? So red is strongly acidic, and then orange is slightly acidic, yellow is even more slightly acidic, right? Green is neutral, and then blue and indigo are basic. So we're starting off with water. So the initial color is green, right? The initial color is green. And when nitrates decompose, right? When group 2 nitrates decompose, right? We get the oxide, we get nitrogen dioxide, and we get oxygen gas, right? So we get nitrogen dioxide and we get oxygen gas. Now nitrogen dioxide is an acidic gas. Nitrogen dioxide is an acidic gas. So we're starting with green because we have neutral water, right? And then we're adding nitrogen dioxide, which is making the water acidic, right? We're getting an acidic solution. So we have a color change from green to red, okay? And down the group, the thermal stability of the nitrates increases. So strontium nitrate is more stable. Okay? Strontium nitrate is more stable, more thermally stable. So that means that calcium nitrate is less stable, it will decompose faster. And if it decomposes faster, it will produce NO2 at a greater rate, and therefore calcium nitrate will cause a quicker color change. So the answer is C. Question number 23 says the equations for 3 reactions involving chlorine or its compounds are listed. Which statement about these equations is correct? Equation 1 describes the formation of a compound used to kill bacteria in drinking water. That's incorrect. Potassium chloride does not kill bacteria. Okay, for killing bacteria, we need the chlorate 1 ion or ClO minus. So statement 1 is incorrect. Okay. Equation 1 does not represent a redox reaction. That is also incorrect because it is a redox reaction, right? We have ClO3 minus here. This is chlorate 5, right? ClO3 minus is the chlorate 5 ion. So chlorine is plus 5 here. Chlorine is 0 here. Oxygen is minus 2 here. Oxygen is 0 here. So we have a redox reaction, right? We have a redox reaction here. So B is incorrect. Equation 2 describes the formation of potassium chlorate 4. Well, we have ClO4 minus here, right? We have ClO4 minus. Again, K plus ClO4 minus. Where chlorine is X, we have 4 oxygens, minus 2 each. Overall is minus 1. So that means X is equal to plus 7. So this is chlorate 7. This is chlorate 7. Okay. This guy over here is chlorate 7, not chlorate 4. Okay. So statement C is also incorrect. Okay. Because again, the oxidation state is in the name, right? The oxidation state of chlorine is in the name. So that's plus 7. Equations 2 and 3 both represent disproportionation reactions. That is correct. Okay. That is correct. Disproportionation is when the same species is simultaneously oxidized and reduced. So here chlorine goes from plus 5 to plus 7 and minus 1. So it's being oxidized to plus 7 from plus 5 and being reduced to minus 1. And in reaction 3, it's going from 0 to minus 1 and plus 5. So it's being reduced from 0 to minus 1 and oxidized from 0 to plus 5. So the answer is D. Nitrogen monoxide is a primary pollutant produced by petrol engines and is found in their exhaust gases. Which reaction occurs in a catalytic converter and decreases the emission of nitrogen monoxide? Nitrogen monoxide reacts with carbon monoxide to give you nitrogen and carbon dioxide. So the answer is just C. Okay? This is an equation that you guys should remember. So here we have question number 25. It says the diagram shows the structure of the naturally occurring molecule cholesterol. Student X stated that the 17 carbon atoms in the 4 rings all lie in the same plane. Student Y said that this molecule displays cis-trans isomerism at the carbon-carbon double bond. Which students are correct? Well, student X is definitely incorrect because we have tetrahedral carbons here, right, in these rings, because the carbon atoms are bonded to 4 atoms, right? This carbon is bonded to 4 atoms, this carbon is bonded to 4 atoms, this carbon is bonded to 4 atoms, right? So all the carbons that are making single bonds are bonded to 4 atoms, so they're all tetrahedral. That means that these rings are non-planar. So student X is correct. Okay, the rings are not planar, they're non-planar, they don't lie in the same plane. And student Y said the molecule displays cis-trans isomerism. He is also incorrect because a carbon-carbon double bond inside a ring does not display cis-trans isomerism. So the answer is B. The drug cortisone has the formula shown. In addition to those chiral centers marked by an asterisk, how many other chiral centers are present in the cortisone molecule? Well, we know that these aren't chiral centers, right? We know that the double bonded carbons aren't chiral centers either, right? Any carbon that's making a double bond, not a chiral center. Any carbon with 2 hydrogens, right? Because we have 2 bonds shown, that means this is a CH2, this is also a CH2. So not a chiral center. This is a chiral center. Again, these are CH2s, not chiral centers. These are already labeled for us. This one is making a double bond, CH2. This one is a chiral center. These are CH2s, so not chiral centers. This one is a chiral center, and then this is making a double bond, so not a chiral center. And this is a CH2, so not a chiral center. So there are 3 additional chiral centers, right? There are 3 additional chiral centers. Question number 27 says but2ene reacts with cold dilute acidified potassium manganate 7 to give product X. But2ene reacts with hot concentrated acidified potassium manganate 7 to give product Y. Which statement about product X and product Y is correct? So first we'll just draw out but2ene. We have CH3, CH, double bond CH, CH3. Now for product X, right, we're reacting but2ene with cold dilute acidified manganate 7, so we're making a diol. We're making a diol, so CH3CHOH and then CHOH and then CH3, right? So this is product X. Okay, this is product X. Right, we get a diol because again, when you use cold dilute acidified manganate 7, right, that's weak oxidation of alkenes. It's an electrophilic addition reaction. We get a diol. We have the addition of 2 OH groups, and then product Y over here, okay, is ethanoic acid. Ethanoic acid. Why? Because we're going to rupture this double bond, right? To make product Y, we're going to rupture the double bond. Why? Because we have strong oxidation. We're using hot concentrated acidified manganate 7. When we use hot concentrated acidified manganate 7 with an alkene, we rupture the double bond. And if the carbon on the double bond, is bonded to one hydrogen, then that carbon becomes a COOH group. So this CH will become a COOH, and then this CH will also become a COOH. So we get CH3COOH, and we get CH3COOH. So what we get is 2 moles of ethanoic acid. So obviously both product X and product Y will not react with 2,4-DNPH, right? This statement is incorrect, and statement B is correct, right? Neither product Y nor product X will react with 2,4-DNPH. 2,4-DNPH is a test for carbonyl compounds. 2,4-DNPH is a test for aldehydes or ketones. Product X and product Y do not have an aldehyde or a ketone. So neither of them will react with 2,4-DNPH. Okay, neither of them will react with 2,4-DNPH. A sequence of reactions takes place. The major product is compound Z. What is compound Z? So we're starting with propanoic acid, that's CH3CH2COOH. We react it with lithium aluminum hydride. That will reduce the carboxylic acid to a primary alcohol. So we end up with CH3, CH2CH2OH, right? That is propan 1-ol. Then we react this propan 1-ol with concentrated sulfuric acid. So that is the dehydration of alcohols, right? Elimination. The mechanism is elimination. We make an alkene. So what we're going to do is we're going to remove the OH and a hydrogen from the neighboring carbon. So we end up with propene. So CH3CH2. Again, we're removing the OH and a hydrogen from the neighboring carbon, and then we're reacting propene with steam. Right? We're reacting propene with steam. When we react propene with steam, we get an alcohol again. But now our major product will be propan 2-ol. Remember, the reason why this is the major product is because the hydrogen will bond to the carbon with more hydrogens. So we end up with a secondary carbocation intermediate. The hydrogen will bond here, we get a secondary carbocation, and then that's where the OH will bond. Right? So the major product will be the hydrogen bonding to the carbon with more hydrogens. The hydrogen will bond to this carbon, so that will become a CH3, and the OH will bond to the carbon with fewer hydrogens. So the answer here is D. Which statement is correct? Bromoethane reacts with aqueous sodium hydroxide to form ethene as a major product. Bromoethane is a halogenoalkane. Okay? And if you want to make ethene, which is an alkene, you have to use NaOH and ethanol. Okay, you have to use NaOH and ethanol for the elimination of halogenoalkanes to form alkenes. If you use NaOH aqueous, you're going to get ethanol. Okay, if you use NaOH aqueous, you get ethanol as your product, not ethene, right? If aqueous NaOH, we get nucleophilic substitution, right? The mechanism, that's hydrolysis of halogenoalkanes. And if you use NaOH and ethanol, then you get elimination to make an alkene. So A is incorrect. 1-chlorobutane reacts more rapidly than 1-bromobutane. That is also incorrect. The reason why is because the CBr bond is weaker than the CCl bond. Right? Which means that bromobutane will react faster. The CBr bond, because it's weaker, will break more easily. So the rate of reaction is faster with 1-bromobutane. 1-chlorobutane will react more slowly. Okay. Hydrolysis of this halogenoalkane occurs by the SN2 mechanism. That is incorrect because this is a tertiary halogenoalkane. Right? The carbon with the halogen is bonded to 3 carbons. And tertiary halogenoalkanes favor the SN1 mechanism. So the answer must be D. This is a primary carbocation, right? The carbon with the positive charge is bonded to just 1 carbon. So we have a primary carbocation, which is less stable than the tertiary carbocation, right? And that is true. A tertiary carbocation, the carbon with the positive charge is bonded to more carbons, and that is more stable due to the positive inductive effect of the alkyl groups. In the hydrolysis of bromoethane by aqueous NaOH, what is the nature of the attacking group and of the leaving group? The attacking group is a nucleophile and the leaving group is also a nucleophile. So let me draw this out. We have bromoethane, which is CH3 CH2Br, right? I'll draw out the mechanism. We have a delta plus, we have a delta minus, right? When aqueous NaOH reacts with a halogenoalkane, we have a nucleophilic substitution. So the hydroxide ion is the nucleophile. It attacks this carbon. This bond breaks at the same time, right? It's a one-step mechanism because it's the SN2 mechanism. It's the SN2 mechanism. Why? Because we have a primary halogenoalkane. Primary halogenoalkanes favor the SN2 mechanism, so it's a one-step mechanism. We end up with ethanol as our product, CH3CH2OH, and we get Br minus, right? So Br minus is your leaving group, okay? Br minus is your leaving group, which is a nucleophile. Okay, it's a nucleophile because it has a lone pair, so it's a lone pair donor. And the attacking group is the hydroxide ion, which is also a nucleophile, right? A nucleophile is a species that donates a lone pair of electrons. Okay, so Br minus is a nucleophile and OH minus is also a nucleophile. So the answer is D. X is an organic compound containing the elements carbon, hydrogen, and oxygen only. The table shows the observations made from 3 chemical tests carried out on X. What is a possible structure of X? Now, X reacts with sodium metal, so that means that it has an OH group, right? Either from a carboxylic acid or from an alcohol. Sodium is a test for the OH group, okay? All 4 compounds here have an OH group. Sodium carbonate is a test for the carboxyl group specifically. Okay, sodium carbonate is a test for the carboxyl group specifically. It will only react with carboxylic acids, which rules out options B and C, right? A has a COOH and D has a COOH. And then it does not react with acidified dichromate 6 in heat. Okay, it does not react with hot acidified dichromate 6. In other words, it cannot undergo oxidation. Now A has a secondary alcohol group, right? The carbon with the OH is bonded to 2 carbons, so this is a secondary alcohol, and D has a tertiary alcohol, right? D has a tertiary alcohol. So A can be oxidized to a ketone, right? A secondary alcohol can be oxidized to a ketone, right? Because the dichromate 6 is remaining orange, it's not reacting, so that means that the alcohol cannot be oxidized, so it must be a tertiary alcohol, so the answer is D. How many moles of oxygen gas are needed for the complete combustion of 1 mole of CH3 thrice COH? You just have to write down the combustion equation. We have C4H10O, right? That's the molecular formula here. We have 3 carbons plus 1 4, 3 times 3 9 plus 1 10 hydrogens and an oxygen. This reacts with O2 to give us CO2 and H2O. And then we just have to balance this. We have 4 carbons on the left. Okay, we're going to start with one of these. So we have 4 carbons on the left. So 4 on the right, we have 10 hydrogens, so that will be 5H2O. And then we have 4 times 2, which is 8, plus 5, that's 13. 13 oxygens on the right. We have 1 here, so we need 12 more, so that will be 6O2. So the answer is just A. Okay. For 1 mole of this guy, we're going to need 6 moles of oxygen. In which pair will each compound give a different visible result with alkaline aqueous iodine? Alkaline aqueous iodine is a test for the CH3 CHOH group or the CH3CO group, right? It only works for either carbonyl compounds or alcohols, right? So it won't work for something like a carboxylic acid, okay? It won't work for something like a carboxylic acid. So it won't work for something like ethanoic acid, but it has to have a CH3CHOH or a CH3CO group, okay? If it's an alcohol, it has to have this group, and if it's an aldehyde or a ketone, it has to have the CH3CO group. Now, the only primary alcohol is if this is a hydrogen, right? So that would be ethanol, and the only aldehyde that gives a positive test is ethanal, which is this guy over here. So both of these will give the same result, right? Both of these will give the same result. So the answer is not A. The answer is not A, right? Now in B, we have ethanal, which again gives a positive result, right? Ethanal gives a positive result because we have the CH3CO group, and Propanone will also give a positive result because we have a CH3CO and then a CH3. So this entire CH3CO group is present, right? This entire CH3CO group is present. Okay. So B is also not the correct answer. C, both of them will not give a positive result. Both of them will not give a positive result. Why? Because as I said, carboxylic acids won't give that result. And here we have a CH3CH2CO. We don't have a CH3CO. We don't have a CH3 directly bonded to a CO here. So that means that the answer must be D, right? We have ethanol, which gives a positive result. We have ethanol, which gives a positive result. And we have propanal, which gives a negative result, right? Because we don't have a CH3CO here. So this will not give us a pale yellow precipitate, right? That's the positive result. Pale yellow precipitate if you have this group or this group present. What happens is that the CH3 breaks off, and gives CHI3, right? Which is triiodomethane. Right, so the product is triiodomethane, and this is a pale yellow precipitate. Okay, it's a pale yellow precipitate. So that's the observation. Which reagent gives a positive result with propanone? Well, we just checked in the previous question. The answer is A. Right, propanone has a CH3CO group. Right, this is propanone. We have the CH3CO CH3, and the products here are CHI3, that's your pale yellow precipitate, and we get a salt of the carboxylic acid. Okay, again, the CH3 breaks off, and then this carbon becomes a carboxylate. Okay, this carbon becomes a COO minus. So we have a CH3CO, and then here we get an O minus. Esters can be hydrolyzed with an aqueous alkali or an aqueous acid to form two products. The table compares the two methods. Which row is correct? Now from alkaline hydrolysis, okay, we get an alcohol plus we get the salt of the acid. And if you use an acid, right, for the hydrolysis, the acidic hydrolysis, we get alcohol plus carboxylic acid. We get alcohol plus carboxylic acid. So A is incorrect, right, because aqueous alkali will give us conversion to a salt and an alcohol, a salt of the organic acid, and an alcohol. So A is definitely incorrect. B, with alkali forms an equilibrium mixture with a salt and an organic acid. Again, that's incorrect. C, we get complete conversion to a salt and an alcohol. D, we get complete conversion to a salt and an alcohol. So it must be C or D. And then with acid, we get a equilibrium mixture with an organic acid and alcohol. This is correct, right? Because the reason this is correct is because acid is used as a catalyst for hydrolysis as well as for esterification. Okay, acid is used as a catalyst for hydrolysis as well as esterification, right? So you're going to have an equilibrium between the organic acid and an alcohol. So the answer is C. Okay, the answer is C. Structural isomerism only should be considered when answering this question. How many compounds with molecular formula C5H11Br are primary halogenoalkanes? Now over here we have to find the number of structural isomers with this molecular formula that are primary halogenoalkanes. Primary halogenoalkanes means we have a CH2Br, right? Because the carbon with the halogen is bonded to just one carbon, right? And two hydrogens. That's what a primary halogenoalkane is. So again, if you want to find the number of structural isomers, we have to think about first what are the types of structural isomers. We have functional group, chain, and position. In this case, we won't have any functional group isomers because they're all halogenoalkanes. So we have to look at chain and position isomers. So we're going to go chain by chain. We're going to start with the 5-carbon chain, right? Now the 5-carbon chain, right? We have 1, 2, 3, 4, 5, and then the bromine has to be at the end. The bromine has to be at the end, right? We have a CH2Br. The bromine can't be in the middle because then it wouldn't be a primary halogenoalkane. So we just have one possibility with a 5-carbon chain. You can put the bromine here or here, it's the same thing, right? 1-bromopentane. Next, we're going to look at a 4-carbon chain. Okay, we're going to look at each chain and look at the different positions that we can have, right? Because we're only looking at chain and position isomers here. We're not looking at functional group isomers because they all have the same functional group. So they have to be chain or position. With a 5 carbon chain, we just have one possibility. Now let's say I had a 4 carbon chain like this. That means that I have a methyl group in the branch, right? I have 1 carbon in the branch, so I have a 4 carbon chain with 1 carbon in the branch. Now again, because I want a primary halogenoalkane, the bromine has to be at the end. So the bromine can be here, right? Or here, that's the same thing. If the bromine is here or here, it's the same thing, right? If you draw it here, you get a 4 carbon chain, methyl on carbon number 2. If you show it here, you get a 4 carbon chain, methyl on carbon number 2. You can also have a Br on the other end. You can also have the Br on the other end, right? Again, this is a primary halogenoalkane. You have a CH2Br, but methyl is on carbon number 3. So here we have 1 bromo 2 methyl. Here we have 1 bromo 3 methyl, right? So these are two different possibilities of the 4 carbon chain. Again, the bromine can't be in the middle because it has to be a primary halogenoalkane. And then you can have a 3 carbon chain, right? In the 3 carbon chain, we're going to have something like this. I have a 3 carbon chain like this. We have 2 methyl groups, and the bromine obviously has to be at the end, right? It doesn't matter if I show it here, 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 or here, it's the same thing. There's only one possibility with a 3 carbon chain, right? If you drew it here, it's the exact same thing. You have a 3 carbon chain with a bromine on carbon 1 and 2 methyl groups on carbon 2. Bromine on carbon 1, 2 methyl groups on carbon 2. So this is 1 bromo and then 2 dimethyl propane, okay? If you drew the bromine here, it's the same thing. 3 carbon chain, 2 methyls on carbon 2, same thing here. If you drew the bromine here, 3 carbon chain, 2 methyls on carbon 2, and so on. So it doesn't matter where you draw the bromine. Okay, it doesn't matter where you show the bromine, it has to be on one of the edge carbons. Okay, so the answer is just A. You just have 4 structural isomers that are primary bromoalkane. So the answer over here is A. Compound Z is formed by the reaction scheme shown. What is the formula of compound Z? So here in reaction 1, we're reacting bromoethane with KCN and ethanol. This is a nucleophilic substitution, right? We're going to make a nitrile, so CH3CH2CN, right? This is a substitution of the bromide with the cyanide, so we end up getting a nitrile. And then we're reacting the nitrile with dilute HCl. That's hydrolysis of nitriles, right? So the nitrile is converted to a carboxylic acid, CH3CH2COOH, right? This is acidic hydrolysis of nitriles. The nitrile is converted to a carboxylic acid. So our final product is propanoic acid. So the answer is D. Hydroxyethanol is heated under reflux with an excess of acidified dichromate 6 until no further oxidation takes place. What is the skeletal formula of the organic product? Now over here we have a CH2OH, right? That's a primary alcohol group. So that will be converted to a carboxylic acid. That will be converted to a carboxylic acid. Then we have a CHO, right? That's an aldehyde that will also be oxidized to a carboxylic acid. So we have CO2H, CO2H. So the skeletal formula of the product will look like this, right? We have 2 carboxyl groups bonded to each other. So the answer here is B. The formula shows a repeat unit of an addition polymer. What is the correct name of the monomer from which this polymer is made? So let's first draw out the repeat unit. We have a CH and a CH, right? We have CH, we have CH, right? We have a CH3 in the side chain on the first carbon, so CH3. We have a CH2, CH3, that's an ethyl group in the side chain here, right? And then we have the continuation bonds. So this is the repeat unit. This is the repeat unit. Since you want to know the name of the monomer, okay, you first get rid of the continuation bonds, right? We draw the monomer by putting a double bond between these 2 carbons, right, along the main chain of the polymer. And then over here we have a 5 carbon chain. We have 1, 2, and then 3, 4, and then 5. So we have a 5 carbon chain, and we have a double bond on carbon number 2. Right? We have a 5 carbon chain, double bond on carbon number 2, which is pent-2ene. So the answer is just C. Right, 5 carbon chain, so that's pent, and then we have a double bond on carbon number 2. Right, double bond between carbons 2 and 3, so that would be pent-2ene. Again, we want to minimize the number of the function groups. We're going to number from this side. Question number 40 says the infrared spectrum of a compound is shown. Which functional group could the compound contain? Well, it is not an alcohol or carboxylic acid, right? Because carboxylic acids have a very broad OHP, Okay, carboxylic acids have a very broad OH peak somewhere in this region, right? So this is the kind of peak that a carboxylic acid has. It has a very broad OH peak that hides the CH peak. We don't have that here. Okay, we don't have that here. And alcohols have this OH peak all the way to the left, which we don't have either, right? A relatively broad peak for alcohols, which is not present either. So it's not alcohol or carboxylic acid. It's not a nitrile either, because for nitrile we should have a peak at 2200 to 2250. Should have a peak at 2200 to 2250, somewhere around here, right? This is around 2200. Okay, we don't have any peak over here, so it's not a nitrile. Okay, so we don't have an OH group. We don't have a C triple bond N. But we do have this peak around 1700, which is for the C double bond O. Okay, we have this peak around 1700, which is for the C double bond O. So that means that the answer over here is ester. Okay, the answer over here is ester. We don't have an OH peak, so it's not alcohol or acid, and we don't have a C triple bond N, so it's not nitrile.